What if the Big Bang was not the beginning of everything, but merely the beginning of our chapter of the universe? For decades, we have been taught that time, space, and matter all burst into existence in a single moment. But physics, when pushed to its limits, begins to whisper a far stranger possibility. What if there was something before the beginning? What if the universe did not emerge from nothing, but from something far deeper, far more fundamental than space and time themselves? Tonight, we are going to explore the edge of known physics, where equations break down, imagination takes over, and science dares to ask its most dangerous question: what came before the Big Bang? When people hear the phrase Big Bang, they instinctively imagine an explosion. A fireball erupting into empty space, scattering galaxies outward like shrapnel. This image is vivid, dramatic, and completely wrong. The Big Bang was not an explosion in space. It was an expansion of space itself. There was no center, no edge, no surrounding emptiness into which matter exploded. Every point in the universe was once compressed into an unimaginably hot, dense state, and space itself began to stretch everywhere at once. Even today, that stretching continues. Galaxies are not flying away because they were blasted outward. They are drifting apart because the fabric of the universe beneath them is expanding. This distinction matters deeply because once we understand that the Big Bang describes the evolution of space and time rather than their absolute creation, an unsettling realization emerges. When physicists run the equations of general relativity backward, they do not arrive at a definitive beginning of everything. Instead, they reach a boundary, a mathematical wall where density becomes infinite, temperatures diverge, and the equations stop making sense. This is known as a singularity, but a singularity is not a physical object. It is a sign that a theory has reached the limits of its applicability. In other words, the Big Bang marks the beginning of our understanding, not necessarily the beginning of reality. Physics has encountered this situation before. Newton's laws work beautifully for everyday motion, but they break down near the speed of light. That breakdown did not mean reality ended. It meant a deeper theory was required. Einstein's relativity replaced Newtonian mechanics in extreme conditions, revealing a richer structure beneath familiar concepts. The same logic applies to the Big Bang. When our equations fail, nature does not vanish. It simply stops speaking a language we currently understand. This is why asking what happened before the Big Bang is not meaningless, it is premature. It is like trying to describe atoms before discovering chemistry or electricity before understanding charge. The absence of a complete theory does not imply the absence of a prior state. It implies that our intellectual tools are incomplete. Modern physics strongly suggests that space and time themselves may not be fundamental. They may be emergent like temperature or pressure, arising from deeper microscopic processes. Consider temperature. Temperature feels fundamental to us. We experience it directly. But temperature does not exist at the level of individual atoms. It emerges only when trillions of particles move collectively. In the same way, time may emerge only when the universe reaches a certain level of complexity. At the deepest level, reality may be timeless. If this is true, then asking what happened before the Big Bang may be like asking what temperature was before atoms existed. The question assumes a framework that may not yet apply. This idea is unsettling because time is woven into our intuition. Cause comes before effect. Birth comes before death, yet physics increasingly suggests that time is not as absolute as it feels. Einstein showed us that time slows down near massive objects and speeds up for fast-moving observers near the Big Bang, where densities and energies were extreme beyond anything we can replicate. Time itself may have behaved in ways that defy our everyday understanding. The beginning of time may not be a sharp edge, but a gradual transition, where the concept of before loses meaning. And yet, the story does not end there. Even if time as we know it emerged at the Big Bang, that does not rule out deeper structures existing beneath it. Quantum physics teaches us that the vacuum is not empty. Even in a state we call nothing, particles flicker in and out of existence, borrowing energy from the uncertainty built into the universe itself. This quantum activity is not a bug in the laws of physics. It is a feature. The universe is restless at its core. If quantum laws apply, not just to particles, but to the universe as a whole, then the Big Bang may have been a quantum event. Instead of a creation from absolute nothingness, it could have been a transition, a fluctuation, that allowed space and time to crystallize out of a deeper, more abstract reality. In this view, The universe did not need a spark from outside. It arose naturally the way bubbles form in boiling water or ripples appear on the surface of a pond. This perspective dramatically reshapes the notion of beginnings. The Big Bang becomes not the ultimate origin, but a phase change, a moment when the universe shifted from one state to another. Before that shift, the laws governing reality may have been entirely different or perhaps more unified. Space and time may have existed only in a blurred, quantum form, fluctuating, wildly unable to sustain structure until conditions stabilize. The difficulty, of course, is that we cannot directly observe this era. Light itself could not travel freely in the earliest moments of the universe. Our most ancient signals, such as the cosmic microwave background, already come from a time long after the initial transition. Yet physics allows us to be detectives, just as geologists infer Earth's history from rock layers. Cosmologists infer the universe's history from subtle patterns imprinted across the sky. Tiny irregularities in cosmic radiation, minute distortions in space, time, and the distribution of galaxies all serve as clues, whispering hints about conditions that existed when the universe was young, and perhaps even before our familiar timeline began. What makes this pursuit extraordinary is that it pushes science to confront its own foundation. We are no longer just studying stars and galaxies, we are questioning the nature of existence itself. Is time fundamental or emergent? Is the universe unique or one of many? Did reality have a beginning, or has it always existed in some form? These are not religious or philosophical questions masquerading as science. They are precise questions framed in mathematical language, constrained by observation and logic. The Big Bang, once thought to be the ultimate answer, has become a doorway. It marks the edge of what we know, not the edge of what is. As our theories evolve, that doorway may widen, revealing a deeper layer of reality beneath space and time. The most important lesson is not that we have solved the mystery, but that the mystery itself has become sharper, more focused, and more profound. The universe is not shutting down inquiry at the Big Bang. It is inviting us to look beyond it, armed with humility, curiosity, and the willingness to rethink the most basic assumptions about reality. When physics descends into the quantum world, common sense quietly leaves the room. Here, the vacuum is not empty, nothingness is unstable, and certainty is replaced by probability. Even in the darkest, coldest regions of space, particles are constantly appearing and disappearing, borrowing energy from the universe, and then returning it, all within the limits allowed by quantum uncertainty. This restless activity is not theoretical speculation. It has been measured, tested, and confirmed in laboratories around the world. The universe, at its most fundamental level, refuses to sit still. And this realization opens a remarkable possibility. If quantum laws govern everything else, why should the birth of the universe be any different? In quantum mechanics, events can occur without a classical cause as long as they obey statistical rules. Radioactive atoms decay without warning. Virtual particles pop into existence spontaneously. These phenomena are not signs of chaos, they are expressions of deeper order. Applied to cosmology, this suggests that the Big Bang may have been a quantum event, a fluctuation that allowed a tiny region of space to inflate into an entire universe. In this view, creation is not miraculous, it is natural. Given enough time, quantum processes will explore every possibility, including the creation of universes. This idea dramatically redefines nothing. In everyday language, nothing means absence. In physics, nothing means a vacuum governed by laws, fields, and probabilities. The laws themselves are something. They structure what can and cannot happen. If the universe emerged from a quantum vacuum, then the real mystery is not how something came from nothing, but why the laws of physics are the way they are. The Big Bang becomes not a violation of logic, but an outcome permitted by it. Once the universe came into existence, something extraordinary happened. Space expanded at an exponential rate driven by a process known as inflation. In a fraction of a second, the universe grew from subatomic scales to macroscopic dimensions. Inflation explains why the universe appears so uniform, why distant regions look remarkably similar despite never having time to communicate. It stretched tiny quantum fluctuations into vast cosmic structures seeding the galaxies we see today. But inflation may not have been a one-time event. According to some models, inflation never completely stops. Instead, it ends in localized regions, creating pocket universes like ours while continuing elsewhere. This process known as eternal inflation, leads to a startling conclusion. Our universe may be just one bubble in a much larger multiverse. Each bubble has its own Big Bang, its own beginning of space and time, and potentially its own physical constants. In this framework, asking what happened before the Big Bang becomes a very different question. Our Big Bang may have been the birth of our local bubble, not the birth of all existence. Before it, inflation may have been raging elsewhere, generating countless other universes. Time itself may extend beyond our cosmic horizon, even if we cannot observe it directly. The universe, or multiverse, may be far older and far larger than our observable region suggests. What makes this idea compelling is that it is not invented to be dramatic. It arises naturally from equations designed to solve real problems in cosmology. Inflation was proposed to explain observable features of the universe, and eternal inflation emerges as a consequence of certain inflationary models. This is how science often advances, not by chasing wild ideas, but by following mathematics wherever it leads, even when it points toward unsettling conclusions. Yet, the multiverse is not an excuse to abandon testability. Even if we cannot observe other universes directly, the process that creates them can leave imprints in our own. Subtle anomalies in the cosmic microwave background, unexpected patterns in the distribution of galaxies, or specific statistical signatures could provide indirect evidence. The universe may carry scars from its earliest moments, revealing hints of a far grander structure beyond what we can see. The idea that our universe might not be unique challenges a deeply rooted intuition. We like to believe that our cosmos is special, that it began in a singular event, and that its laws are finely tuned for our existence. But physics has a history of dismantling such assumptions. Earth was once thought to be the center of everything. Then the sun took that role. Then the galaxy. Each time, our sense of uniqueness diminished, and our understanding grew. If eternal inflation is correct, then the Big Bang is not the ultimate beginning, but a local event in a much larger cosmic process. Our universe becomes one realization among many, governed by deeper principles that transcend space and time as we know them. This does not make our existence meaningless. On the contrary, it makes it more remarkable. Out of an immense cosmic landscape, we find ourselves in a universe capable of producing stars, planets, life, and consciousness. These ideas push science to its limits, but they do not abandon rigor. They're framed in equations, constrained by observation and refined by debate. They invite skepticism, testing, and revision. The goal is not to replace one mystery with another, but to build a coherent picture that connects the smallest quantum fluctuations to the largest cosmic structures. In doing so, physics dares to address the most profound question of all, not just how the universe evolved, but why a universe like ours exists at all. As physics pushes beyond the familiar boundaries of particles and forces, it begins to hint at dimensions beyond the three of space and one of time that shape our daily experience. This is not fantasy, but a natural consequence of trying to unify the laws of nature. When mathematicians and physicists attempt to merge quantum mechanics with gravity, though, equations resist simplicity unless reality is allowed to have additional dimensions. In this framework, the universe we perceive may be only a thin slice of a far richer structure, much like a two-dimensional. Being living on the surface of a sheet of paper would be unaware of the third dimension above and below. In theories that explore these extra dimensions, the fundamental constituents of nature are not point-like particles, but tiny vibrating strings. Each vibration corresponds to a different particle, much like different notes played on a violin string create different sounds. Space itself becomes an arena where these strings move, interact, and sometimes stretch across dimensions we cannot see. This shift in perspective transforms the Big Bang from a singular act of creation into a dynamic event emerging from higher dimensional physics. Within this view, our universe may be embedded in a higher dimensional space, sometimes called the bulk, while all the familiar forces and particles are confined to a lower dimensional surface. This surface can be thought of as a cosmic membrane or brain. These brains are not static. They can move, vibrate, and even collide. When such collisions occur, the energy release can be immense and enough to give rise to an event that, from within the brain, looks exactly like a Big Bang. In this scenario, the origin of our universe is not a creation from nothing, but a collision between higher dimensional structures governed by well-defined physical laws. The universe begins not with a singularity, but with interaction. Space and time unfold as consequences of that event, while the deeper reality continues to exist beyond our perceptual reach. This idea elegantly sidesteps the notion of an absolute beginning replacing with a process embedded in a timeless or pre-existing framework. These higher dimensional models also open the door to a universe with a memory. If our cosmos emerged from a brain collision, subtle traces of that event might still be detectable. Patterns in cosmic radiation, slight asymmetries in the large-scale structure of the universe, or specific signatures in gravitational waves could serve as fossils of a pre-Big Bang state. The universe itself becomes an archive, preserving hints of its own origin in the distribution of matter and energy across vast distances. Equally provocative is the idea that the universe may not have begun at all, at least not in the way we typically imagine. Some models suggest that the cosmos undergoes endless cycles of expansion and contraction. In this cyclic view, the universe expands, cools, and eventually reverses course, collapsing back into a dense state that triggers a new expansion. Each Big Bang becomes a transition rather than a starting point, and time stretches infinitely in both directions. This vision restores a sense of continuity to existence. Instead of a universe abruptly appearing out of nothing, we have a cosmos that renews itself, evolving through repeating phases. The laws of physics remain intact across cycles, even as structures dissolve and reform. Galaxies, stars, and planets are temporary arrangements in a much longer cosmic rhythm. The universe breathes, expanding and contracting, shaping and reshaping itself over unimaginable timescales. What makes these ideas compelling is not their drama but their necessity. Singularities signal failure, not triumph. They tell us where our theories break down. Cyclic and higher dimensional models attempt to remove these breakdowns by embedding the universe in a larger, more coherent framework. They do not claim final truth. They offer plausible extensions of known physics into regimes we have yet to fully explore. These concepts also force us to confront the limits of intuition. Human intuition evolved to navigate forests and savannas, not higher dimensional spaces or eternal cosmic cycles. Yet, mathematics allows us to transcend those limits. Equations become our senses, revealing structures we cannot visualize but can understand. In this sense, theoretical physics is not an escape from reality, but a deeper engagement with it. If the universe truly operates through higher dimensions or endless cycles, then the question of beginnings takes on a new meaning. There may never have been a moment when existence emerged from nothing. Instead, there may have been transitions, interactions, and transformations governed by timeless laws. The Big Bang, rather than being the birth of everything, becomes a chapter break in an infinitely long story, one written not in words, but in geometry, vibration, and motion across dimensions beyond our immediate perception. If these ideas about the universe's origin are correct, then the cosmos itself becomes a kind of message left behind by its own birth. Space is not silent. It carries memories. The faint glow of the cosmic microwave background, the oldest light we can observe, is more than a relic of a hot, dense past. It is a snapshot of the universe when it was still an infant, preserving tiny irregularities that later grew into galaxies and clusters. These irregularities are not random noise, they are encoded information. They reflect processes that occurred at energies far beyond anything we can reproduce on Earth, possibly even processes that predate our familiar notion of time. Physicists study these patterns with extraordinary care because they may contain fingerprints of events that occurred before the Big Bang as we understand it. Slight asymmetries, unusual alignments, or unexplained anomalies could point toward earlier cosmic phases, collisions with other universes, or transitions from higher dimensional states. Gravitational waves, ripples in space-time itself, are particularly promising messengers. Unlike light, they travel almost unimpeded through the universe, carrying pristine information from the earliest moments of existence. Detecting specific gravitational wave signatures could provide direct evidence of inflation, cyclic behavior, or higher dimensional interactions. This approach transforms cosmology into a form of archaeology. We cannot travel back in time, but we can read the imprints left behind. Every improvement in observational technology sharpens our view of the past. Satellites mapping cosmic radiation with increasing precision, detectors listening for gravitational waves, and surveys charting the large-scale structure of the universe all contribute pieces to that same puzzle. The universe becomes its own experiment, continuously revealing data to those who know how to ask the right questions. Yet the implications of this search extend far beyond technical details. If evidence accumulates that our universe had a prehistory, then our conception of reality must expand. Time may not be a single linear arrow beginning at a fixed point. It may be layered, emergent, or cyclical. Space may not be the ultimate stage on which events unfold, but a manifestation of deeper processes. These ideas challenge not only science, but philosophy, theology, and our sense of identity. There is a temptation to view such possibilities as diminishing human significance. If our universe is one among many, or one cycle among countless others, does our existence matter? Physics suggests the opposite. Meaning is not derived from uniqueness, but from complexity. A universe capable of producing conscious beings is already extraordinary, regardless of how many other universes exist. Understanding that we are part of a larger cosmic structure does not erase our importance, it contextualizes it. At the same time, these ideas impose a responsibility. As our theories grow more powerful, so does the need for intellectual discipline. Not every speculative idea will survive experimental scrutiny. Many will fail. That is not a weakness of science, it is its strength. Science advances by proposing bold ideas and then subjecting them to relentless testing. Only those that withstand this process remain. The search for what came before the Big Bang is not about replacing one myth with another. It is about extending our framework of understanding while remaining anchored to evidence. This is why the future of cosmology depends as much on education as on technology. To navigate these ideas responsibly, society must understand how science works, how hypotheses are formed, tested, refined, or discarded. In an age of instant information and manufactured certainty, the patience of science stands in sharp contrast. It teaches us to live with uncertainty without surrendering to confusion. The greatest lesson of all may be humility. The universe has repeatedly surprised us. Every time we believed we had reached the end of explanation, new layers of reality revealed themselves. The Big Bang was once thought to be the final word. Now it appears to be a gateway. What lies beyond that gateway remains uncertain, but uncertainty is not ignorance. It is the frontier. In exploring what might have existed before the Big Bang, we are not merely probing the origin of the universe. We are redefining what it means to ask a scientific question. We are learning that reality may be deeper, more structured, and more interconnected than our intuition suggests. And in that realization, we find not despair, but inspiration. A reminder that the universe is not only stranger than we imagine, but stranger than we can imagine, yet still governed by laws we are slowly, patiently learning to understand. When we ask what might have existed before the Big Bang, we are really asking how deep reality goes. The answers physics offers do not close the story, they open it. They show us that the universe may be far older, richer, and more complex than a single moment of creation. And that space and time themselves could be part of a much larger structure still waiting to be understood. What matters most is not whether we already have the final answer, but that we now have the tools, the curiosity, and the courage to keep asking the question. Each discovery brings us closer to understanding not just where the universe came from, but how humanity fits into a cosmos that is still unfolding. Thank you for taking this journey, for your curiosity, and for choosing to explore these ideas through science and reason. Your willingness to think deeply, question carefully, and wonder responsibly is what keeps real discovery alive. Thank you for watching and for being part of this exploration of the universe.